Okay, so I think it's time to start. So this is the fourth week of the live tutorial session. So today we'll be discussing mostly this generating set and linear independence and some cases the basis. So let me again start with the basic notion that will be used today. Uh, so first with generating system. So generating system. So everywhere, so suppose first we always assume that suppose B be a vector space. Vector space with over the field K, over field K. Okay, then a generating system for the vector space V means that so it is a collection of vectors, say V alpha, or some indexing alpha belongs to some indexing set I, such that for any vector in V I can write them as a linear combination of vectors of this V alpha. Okay, for any V belongs to capital V, there exist suppose C alpha belongs to the field K, such that this V equal to sum over C alpha V alpha, where only finitely many C alphas are non-zero. Okay, so in this case we call this V alpha is a generating set for the vector space V. Okay, so this is first one. Then we also define linear independence when we call is system like collection of vectors in a vector space V is linearly independent. So linearly independent. So a collection of set vectors, same to V alpha, or alpha belongs to some index set I, is are called linearly independent if I consider like any linear combination of this V alpha, so C alpha V alpha, this equal to 0 for alpha belongs to I. By to make sense this, already I am assuming that finitely many C alphas are non-zero. So this, then C alpha equal to 0 for all alpha belongs to I. Okay, so this is called linearly independent in vectors. And then what is basis for a vector space? So basis of V. So basis of V we call again a collection V alpha. So a collection of vectors v alpha, alpha belongs to I, are said to form a basis of V if it generates V, it is a generating system of V, like linearly independent generating system. If it is a linearly independent generating system. So from there, so like I can write any vector of the vector space V as linear combination of the vectors this V alpha, such that the representation is unique, like the constant C alpha must be unique. That is guaranteed by the linearly independent. That is like a corollary of this thing, that whenever we have a linearly independent set that generates a vector space, then the coefficient as you write V in the coefficient like linear combination of those vectors, the coefficient will be unique. Okay, so this thing we will only mostly use for today's tutorial. So then let's go to the first question. So first question is, suppose you have three distinct primes number p1, p2, p3. Prime numbers, in natural number, they are natural numbers such that only divisors of them are 1 and themselves. Like p1 can only thing that can divide p1 is 1 and p1 in the division in natural number set. Also, like another thing is that whenever any number any prime number divides another number, like product of two numbers, then at least p divides at least one of them. Those like things you have seen. So you are given three distinct prime numbers, then you need to show that if you take the square root of them, they are linearly independent over Q. Okay, so how to proceed? Any idea? Okay, so then let me proceed. So you are given three distinct prime numbers, right? So I need to show this is linearly independent over the field Q. So this p1, p2 root p1 root p2 root p3 are linearly they are irrational number, right? So, and we are considering everything as a vector space over Q, whatever, like R or C, whatever. Okay, so to show linearly independent, we must consider that for so suppose, because look here, that if you want to show linearly independent, whenever you consider some linear sum of those things, then you must have C alpha equal to 0. Okay, so let's consider summation of Ci root Pi, here I equal to 1 to n, 1 to 3, sorry, this equal to 0. Consider this, where this C1, C2, C3, this belongs to Q, right? That's what we so here's this C alpha belongs to your field K. Okay, so I need to show that each of these C1, C2, C3 is equal to 0. So we can just like use the irrationalities of this root p1, root p2, root p3. So I can write it like in the form root p1 plus c2 root p2 equal to minus c2 root p3. Then square it, and you will see that this is c1 square p1 plus c2 square p2. So a plus b whole square, a square plus b square plus 2ab. So this is 2c1 c2 root over of p1 times root over of p2, that is same as p1 p2, and this is, in this side you get c2 square p3. Now if you arrange this thing, like take the all the rational thing in one side and keep the rational irrational part in other side. So in this case root over p1 p2 is irrational, so 2c1 c2 root p1 p2 is, or sorry, this is c3, so c3 square p3 minus c1 square p1 minus c2 square p2, and so this is by squaring both sides. So if now, if in one side this is a rational element, right? This belongs to q, rational number, because c1 c2 c3 all of them belongs to q, so their square belongs to q, and then this p1 p2 p3 also belongs to q, so they are like any combination of them like product and combination, they also belongs to q, because q is itself a field in particular, like vector space over itself. So this belongs to q, but in this side this 2 c1 c2 obviously belongs to q, but root over of p1 p2 that does not belongs to q. So if this c1 c2 is non-zero, then this side is irrational, right? But this side is rational, and the intersection between, so if c1 c2 not equal to 0, then 2 c1 c2 root p1 p2 this belongs to q complement, that means irrational. Okay, so this is simply because this is a irrational number, so if it is rational, then this root over of p1 p2 is also becomes rational, because this 2 c1 c2 is rational, so this must be rational. So this thing I can write, so as root p1 p2 this belongs to q complement, and 2 c1 c2 belongs to q, and q is field, and q is field. So this is non-zero, I also assume, so that's why its inverse exists there, so that is like contradiction you will get. Okay, so this thing belongs to q. So on one hand you have this belongs to q complement, on the other hand this belongs to q, which is a contradiction. But c3 square p3 minus c1 square p1 q, and these two are equal, 2 and c1 c2 p1 p2 c p2. So this implies like q intersection q complement not equal to phi, which is a contradiction, because they are disjoint set, so their intersection cannot be, so which is a contradiction. Hence thus we must have c1 c2 product c1 c2 is 0, so thus c1 c2, because we get this contradiction because of this reason, c1 c2 non-zero, so we must have c1 c2 equal to 0, and you are in field, so at least one of them, like they c1 c2 belongs to q, and q is field, in particular integral domain, so at least one of c1 and c2 must be 0, so this implies c1 equal to 0, or C2 equal to 0. Okay, but if C1 equal to 0, now again consider like if C1 equal to 0, then if I put in this relation, I'll get like in the square relation, if C1 equal to 0, then we have, then from this 1, then from 1 we have, but we have this is also greater than, so C2 square P2 equal to C3 square P3. So in this case again, like I will use that P2 is not equal to P3, they are distinct. So that means that P2 must divide this C3 square P3. So that means it will divide at C3 square or P3, because P2 is prime number, but P2 cannot divide P3. So P2 must divide C3 square, but C3 square again P2 divides C3 square implies it divides C3, because again due to prime number thing. Okay, so okay, so this implies P2 divides C2 square, C3 square as P2 not equal to P3 is a prime. Right, so this implies P2 divides C3, or in like I can directly write it like this belongs to C3. So if it divides C3, then I will get that on one hand, so let's say this is equal to some K, say, okay, both are equal, so this implies I can write C3 equal to some K1 P2. This implies from this relation K equal to C3 square P3. So this implies K equal to C3 square P3 equal to K1 square P2 square P3. So here the like look at the at least coefficient. So this exponent of this P2, this is at least 2, right, or some power of 2. But also on the other hand, also K equal to, I know that it is C2 square P2, C2 square P2. So in this here again note that this P2 here, the exponent of this P2 which is prime, so here the exponent can always be odd, right, because already here the exponent of P1 is 1, and if if P2 divides C2 square also, then the power of P2 in the total this element K is some 2K plus 1, but in this case you only have some 2P for some P, like any natural number P. So in this case, but also this, so here you have the exponent of P2 is even, okay, and in this case exponent of P2 is odd, right, but so that's so thus by fundamental theorem of sorry, fundamental theorem of arithmetic. We must have C1 equal to C2 equal to 0, because what fundamental theorem of arithmetic says that for each positive number, k is clearly positive number, so for each positive number you can write that as a some power product of powers of prime number. But in this case you see that you, at least for P2, in one hand you get the representation it is even, on the other hand you get the representation as P2 prime, the prime P2 is odd. That cannot happen unless your this total k is 0, right? So that's why you get that. Okay, so by fundamental theorem calculus we must arithmetic we must have C1 equal to C2 equal to 0. Okay, so once we get C1 C2 0 already, okay, so not C1 C2, in this case our C2 C3, right? So this is C2 C3, sorry, because this k can be 0 only if P2 and P3 is non-zero. So either C3 square equal to 0, C2 square equal to 0, both of them should be 0. So that means C2 equal to C3 equal to 0, and by our case we already assume C1 equal to 0. This implies that C1 equal to C2 equal to C3 equal to 0, which I wanted to show that to show this is linearly independent. So this is one case. Similarly, if we consider the C2 equal to 0, so similarly if C2 equal to 0, then we can prove the same way. We can prove that C1 equal to C3 equal to 0. That is again same as C1, C2, C3 all are 0. Hence, in either cases, like this C1 root P1 plus C2 root P2 plus C3 root P3 equal to 0 implies that C1 equal to C2 equal to C3 equal to 0. So for C1 C2, for C1 C2 C3 belongs to rational number Q, right? And P1 P2 P3 distinct. Okay, so hence that means root P1 root P2 root P3 are linearly independent over rational number Q. Okay, so hope this is fine. So it is like exactly just following the irrational. First we deduce that at least one of them is 0 by using the irrationality of root P1 P2, and then again use the fundamental theorem of arithmetic to conclude that other two also be 0 if either of them is 0. Okay, so a similar question you will find in the assignment which you need to submit. Okay, so hope this is fine. If anyone have any question, okay, so then I'll proceed to the next one. So next question is again related to linearly independence and generating system. Okay, so first you suppose that x1, x2, xn and x are elements of a vector space V over a field K. Then we need to prove that if x1, x2, xn are linearly independent, then the family this x1, x2, xn and their sum like x1 plus x2 plus xn is linearly dependent over K. But any n of these vectors are linearly independent over K. So, so you are given, so again, so do anyone have any comment or any idea how to proceed? The process is exactly the same. So again, linearly independent is given, you need to show that this is linearly dependent. But recall that linearly dependent means it is not linearly independent. That means if I have like in the relation, if I consider c1 x1 plus cn plus c2 x2 plus cn xn plus some c times x1 plus x2 plus xn for ci and c belongs to the field K, then I always don't have this, all this cy is 0 and c is 0. So there exists non-zero choice of ci's and c such that this relation still hold to be 0. Okay, so in this case you can see easily that if I add, like take the coefficient c1 c2 cn, all of them 1, and this coefficient of c this x1 plus x2 plus xn is -1, then this clearly add up to 0. So here for the first thing it is easy to see that there we don't need any linearly independent or anything. So here x1 plus x2 plus xn plus, so here the coefficient are all -1, here the coefficient is sorry 1, and here the coefficient is x1 plus x2 plus dot dot plus xn. So this coefficient is -1, then it is clearly add up to 0. So that means the coefficient all are non-zero, but you get add up to 0. So this implies this x1 x2 xn and x1 plus x2 plus xn are linearly dependent, sorry, dependent over K, because K has 1 and -1 elements. I am taking over that. So in other way, you know that linearly independence means that any one of them, at least one of the vector of the collection, you can write them as combination of the other vector, which is indeed the case. In this case, x1 plus x2 plus xn is linear combination of x1 plus x2 plus xn. Trivially true. So this is linearly dependent. But if you remove any of the any one of these elements from the collection, that you will get linearly independent vector. So one thing is to there are n plus 1 vectors, but you are asked to take only n vectors from them, so you need to delete one of them vector. So if I consider, so there are only n plus 1 many choices, I can delete x1 or x2 or xn or x1 plus x2 plus xn. So if I delete this x1 plus x2 plus xn, then x1 plus x1 comma x2 comma xn, they are already linearly independent by the condition. Okay, so if we consider this set, consider x1 dot dot xn n vectors in V, then they are linearly independent. Independent by hypothesis. Okay. Now if I delete except that thing, so if we consider any x1 x2 x1 through xn except one some xi and together with x1 plus x2 plus xn, so consider x1 dot dot xi minus 1 xi plus 1. So I'm not considering the xith vector, and then again all the way up to xn, and then their sum. Xn. Here I'm considering the all this vector. So this is also another possible n vectors. So n vectors in V. So like for any I equal to, I can take any I to be like 2 2, or I equal to 2 3, all the way up to n, right? Okay, so if I take sorry, this is 1 to n minus 1, yeah, 1 to n minus 1. So then also I need to check that if I consider this sum of Ci, or let's Cj xj, j runs from 1 to n, but j is not equal to I, plus some c times x1 plus x2 plus dot dot xn. This is another vector equal to, if I consider this, then this equal to 0 implies I can like rearrange all the things. I'll get that this is, because each of them has like x1 through xn, except the xith position you have the coefficient for xj to be cj plus c, right? So I can, this sum is same as j equal to 1 to n, j not equal to I, and coefficient of this is cj plus c xj, plus the only coefficient for xi is c, so cxi equal to 0. But by the given condition, you know that this x1 through xn, they forms linearly independent set, and you are considering a linear combination of them, so that is 0. So by linearly independent, I will must have that all the coefficient of this x1 through xn is 0. So in particular the coefficient of xi is only c, so c is 0. Okay, so that will again imply that, so this implies that cj plus c equal to 0 for j equal to 1 to dot dot j minus I minus 1, I plus 1, all the way up to n, and c equal to 0, right, for this thing. So this is by using linearly independence of x1 comma up to xn. Okay, so but this implies c, if c is 0, then this is implies all the cj's are 0 for j equal to 1 to this thing, right? So this implies cj equal to c equal to 0 for j equal to 1 to I minus 1, I plus 1, n. Okay, so that was we wanted to show that consider this thing. So for cj comma c belongs to k, so thus these vectors are also linearly independent. Thus xn, x1 plus x2 plus dot dot xn are linearly independent. Then for any choice, like for any, for I equal to, for any I equal to 1 2 up to n minus 1. Okay, because that's the only way to get n vectors from this n plus 1 vector. I can delete x1, x2, xn, or x1 plus x2 plus xn. So in the first case it is independent, in this case also independent, hence any n vectors of this collection xn x1 plus x2 plus dot xn are linearly independent. Right. So that's the thing we need to check over K, obviously. Okay, so this is easy one. I think everyone is happy with it. Okay, so then similar question, the B part is with the same setting. If you have that x1, x2, xn and x are linearly independent over K, then or then x1, x2, xn are linearly independent and x does not belongs to the span of x1, x2, xn, and also the conversely is also true. So here the same thing, like forward, but if we assume that x1, x2, xn and x are linearly independent, so xn comma x are linearly independent. So I'll shortly use this as Li notation. Okay, if this is linearly independent, then I need to show that these x1, x2, xn are linearly independent, but that is by trivially too. Like if x1, x2, xn, like by contradiction, if तो is तो are not linearly independent, then we must have a equation with Ci xi equal to 0, I equal to 1 to n for some non-zero Ci belongs to K, the field K, right? Fine. So this is exactly the not linearly independent means. But if this is the case, this implies I can add this x to this relation simply by taking this coefficient of x to be 0. So this implies I can write Ci xi plus 0 times x equal to 0 for I equal to 1 to n. This is true for some non-zero Ci belongs to K, which is a contradiction because by our choice this x1, x2, xn is linearly independent. So any linear relation you consider that can only be 0 if all the coefficient is 0, which is a contradiction to the hypothesis. Fine. So we must have this. So this implies your x1, x2, xn are linearly independent. But also you need to show that this x does not belongs to linear span of x1. So again, if x belongs to this span, like that means kx1 plus the vector space generated by x1, x2, xn, and then take their like sum of those vector spaces. If then I can write x as some Ci xi because this belongs to this sum, so I must have some choice of C1, C2, Cn for Ci belongs to K, and K is like x is this forms a linearly, so x cannot be 0. So for xi belongs to with with some Ci non-zero, because if all of the Ci are 0, then x is 0, but if x is 0, then this set cannot be linearly independent, right? Because 0 I can write in the this cannot be linearly independent. Like I can write like all the coefficient of x1 x2 xn is 0, and I can put any coefficient for the 0 vector like 100 1 or what thing. So 0 cannot be part of a linearly independent set, so we must have for some Ci non-zero. So but this relation again implies that you have a thing that this is Ci xi I equal to 1 to n plus of minus 1 of x equal to 0. So clearly this coefficient of x is minus 1, so this is like non-zero. This is the non-zero coefficient, and also you know here some coefficient of Ci must be 0. So again, which is a contradiction to the hypothesis. Okay, so thus this implies x does not belongs to kx1 plus dot kxn. Okay, so you have, whenever you have this x1 x2 xn linearly independent over k, you must have x1 x2 xn or linearly independent. Like any in general, any subset of a linearly independent set is linearly independent. You can prove exactly using the same like argument. Also SAT did this thing in class, I think. And also the other vector cannot be linear combination of the other vectors, any vectors of this thing. Okay, so this is a simple simple thing, almost you like comes from the definition of linearly independentness. Okay, so next again consider similar question. I'll leave this question for you. It is almost exactly the same, the contrapositive way. If you have generating system instead of the like linearly independent, if you have a generating system x1 x2 xn of v, that means every element of v you can write in the linear sum of this x1 x2 xn. Then this x1 sum, like if you add one more vector, that also a generating system. That is simple because I can already write any vector in the form of linear sum of x1 x2 xn. So I can take simply the coefficient for x to be 0, and x belongs to this thing because x belongs to the vector space v itself. So it must be a linear combination of x1 x2 xn, because x1 x2 xn is generating set. So I'm just leaving this. Everyone I think can do this. So let's go to the next question, which is related to the polynomial function, like basic polynomial function which forms a basis in the polynomial set. Okay, so suppose k is a field. Okay, so k is a field, and you have a subset D of k, and n belongs to n. Then we need to show that the power function Ti restricted to D. Ti function makes sense because I can take any element of the field k and like multiply it I times for any I belongs to, let's say, n. So this makes sense, and 0th degree means that it's simply 1. They are linearly independent over k in the vector space kd, because this forms a vector space, and their elements, these elements are like elements of this k power d again k valued function on D. This is possible only if and only if D has at least n elements. Okay, so that we need to show again. So consider this direction, that means okay, so consider the other direction, that is the easier way. So suppose D has at least n element, at least n elements, and you are considering this function. So considering the function ti restricted to d for, so all this set I am considering I equal to 0, 1, 2 up to n minus 1 for any n belongs to the natural number set. So natural number set again means that it start with 1 at least. Okay, so this set is linearly independent. I need to show. So to show is linearly independent. So again we consider the linear sum of as a k vector space, because k power k d, so all k value function on d are k vector space. So I'll consider this ci ti equal to 0 for I equal to 0 to n minus 1 for ci belongs to the vector space field k. Okay, so this is again this sum of this thing is again a function, right? And sorry, so I mean this is not t power I. Okay, so this is again a polynomial function, like as a polynomial power function, like polynomial function over the field k on the subset d. So and this is true for like all the, and so this is as a function t, let's say ft. So this as a function, or let me write in this form that you have a function f from d to k defined by ft equal to sum of ci t power I equal to 0 to n minus 1. So h, because this is identically 0, right? So whatever t I put, that is 0. So h like because d has at least n elements, so has at least n roots, right? N roots. That means at least n points this ft becomes 0. But see that this is a n minus 1 degree polynomial. So by fundamental theorem of algebra we know, like repeated application of that thing, like it can have at most n minus 1 0, right? Because this degree is n minus 1. But here you are saying that this is n roots, which is a contradiction. So which is a contradiction to the fundamental theorem of algebra. Contradiction to theorem of algebra, unless all this ci is 0, right? Or yes, so unless all ci equal to 0, or I should write unless ci equal to 0 for all I equal to 1 to up to n minus 1. So this implies that c1 c2 equal to cn minus 1 equal to, or c0, sorry, c0 c1 up to cn minus 1 equal to 0. So this implies that this function t power I restricted to d I equal to 0 n minus 1 is linearly independent, right? So for the converse part, like if I consider this function linearly independent, then I must show that it has at least n elements, right? Suppose it has like less than uh, less than n elements, then like I can consider like D has at least n elements. So to the contradiction I can assume that it has less than n elements, and on there I'll consider this function. So I need to show that that must be linearly dependent, then I'll be done, right? So okay, so for the forward part, so I will assume that t power I restricted to D, I equal to 0 1 to n minus 1 or is linearly independent. So need to show that the number of element in D, so that denote that cardinality, that is to show mod D is greater equal to n, right? Suppose not, then number of elements in D is strictly less than n, right? Now this function, if I say, so I need to show that this function, if I consider the linear sum, that will be 0 for like at least for some non-zero Ci's. But then again you can, like, if you instead of D, if you would have considered K, and K has less than n elements, so simpler case, if you say simpler case, that cardinality of K, so simpler case was that case K equal to D, then number of element in K is less than n. This implies, because in a finite field, or any infinite, in particular infinite group, so this implies that t power n minus 1 will be equal to 1, right? So this is strictly less than 1. So and so like if I take the order of that thing, like K has order K, for K small k, K is less than n, then all the element of K will satisfy t power K equal to 1, for because any finite group, by Lagrange theorem, any finite group has like order, at most the order of the group. So this equal to 1, or I can particularly say that this is up to K equal to 1 for all t belongs to K. So in particular I can write this function, one function is 1, another function in t power mod K, these two things. So this I can write this simply as 1 plus all the up to t power 1 all the way up to like at some point you have minus 1 into t power mod K, and plus all other at 0 times this thing, plus 0, this thing equal to 0, right? Because this 1 minus t power K is 0. So this is happening. So this is for like t power n minus 1, 0 into t power n minus 1. So this is happening for like this collection. So this implies that this collection is, so it's not linearly independent, right? So contradiction to the hypothesis. Okay, so you just have to need to modify this case to the case for any subset of K, So again, as I'm like a bit of short of time, so I'll leave it to you to think of it, like in the in the other case when k d is a subset of k, and so this thing. So in this simpler case, at least we must have that mod k greater equal to n. Okay. Okay, so for d strictly like not equal to k, check it. So I'm leaving it here. Okay, for the other part, like I trying to go over the other two others problem at least. So I'll just quickly go over them, like give the hint, and already in the like assignment it is already given the hint, but I'm just elaborate those hints a bit. Okay, so here the hint is like what you need to show that if you have a infinite field, so in the assignment problem this infinite field is missed, but this is required because of this thing actually you will use. So this thing you see that if you have the field kx which consists of all the polynomials over the field k, and kxm are the all polynomials vector space of the polynomials of degree less than m. Okay, then you consider like a sequence of polynomials fn whose degree is at most n, like then if this f0 f2 up to fn minus 1 is a k basis of the subspace kxm, then you must have this degree of fi equal to I for all I equal to 0 to m minus 1, or also the converse way that if you have degree of fi equal to I, then this must forms a k basis for the subspace this. So two way. So one way that this is a k basis of the subspace is of this kxm, to show that this you need to show that this generates your this vector space kxm, and also these elements are linearly independent, right? So for this part, if your degree of fi is okay, so first thing note that this using the previous thing, previous problem, that in this case you can take this x1 or not x1, just x1 x square up to x m minus 1. So this forms a basis of kxm. Okay, and this forms a basis, so I can this f0 f2 fm minus 1 like belongs to your kxm, so I can write this fi, or let's say fj equal to linear sum of this 1 x square xm minus 1, but by the degree restriction the degree of fi is less equal to I, so I must have the other coefficient of this higher I, that must be 0. So fj of x it can be written as cj of or like ji I equal to 0 to j, because it can be at most degree j. So this thing, sorry, I xi. Okay, now you use like you can use this thing to the problem given in assignment like 4.2, or this thing that this forms a basis. Then if you can write them as like in this fashion, like f0 must be some c0 times 1 f1 is, or c0 1 0 or 0 0, sorry, by this notation f0 is c0 0 1, this is 1 0 into 1 plus 1 1 into x f2 equal to c20 into 1 plus c21 into x plus c22 into x square and so on. So if you have this thing, then this forms a k basis if and only if, so using a problem in assignment thing, this forms a basis if and only if the leading coefficient is c00, c11, cnn. So f0 fm minus 1 forms a basis if and only if this coefficient is CII. So product of this CII I equal to 0 to m minus 1, this is not equal to 0. But if this is not equal to 0, that means none of the CII is 0. But CII is not 0, that means the degree of fj is j, right? So I for okay, this is fine. So this implies that, so this is if and only by the 4.2, so degree of fj is exactly equal to j, or degree of fi is exactly equal to j. Okay, so that's all for today. So we'll discuss some of those remaining problems on the next day. Okay, so for the time being, you can like try this question if you want. We'll discuss them in, they are related, and we'll discuss these problems related to the other some problem, like using this problem we'll discuss some other problem. So okay, so that's all for today. We'll meet next week again.